Hi everyone, my name is Maya and my partner for this project is Sakib. The goal of this project is to figure out how loud a propeller is when spun at different RPMs. Here I have Workbench open and the first thing we do is create Fluent project, and then we're going to import some geometry. So I have a propeller step file, and then we're going to edit this in Design Modeler. So in geometry we're going to make two zones. We have an inner rotating disc and an outer zone. To see our propeller, we hit generate. Okay. So we're going to first make the disc. Go to sketching, sketch a circle. Let's make this 0.27 meters. Okay. And then we're going to extrude this. It will be symmetric. We want it to be 0.01 in depth. You can see. Interesting. I didn't select a geometry there. Okay, or a sketch. Alright, now you see that. And then the next thing we're going to do is we're going to create the non-rotating zone. So we can create a rectangle. Alright, that is all dimensioned, so we can now extrude that as well. Alright, this will be symmetric, and we want it to be 0.5 meter tall. Okay, hit generate. Oh, we'll make it a frozen. Okay, great. So now you can see we have three bodies. We have the propeller and two solids. So it's not confusing. I'm going to name this the disc, and I'm going to name this outer domain. Okay. So now we're going to do two Boolean operations. So create Boolean. We want it to subtract. So our target is this outer zone, and the tool is the disk. And we want to save that disk for later. And once we generate that, we can hide these other bodies. And what you see is you can see that disk is subtracted out of the domain. So the second Boolean we're going to do is we're going to subtract the propeller from the disk. So the target is the disk, tool bodies is the propeller. Generate, and you can see that body disappeared. And we have the disk and the outer domain. When we hide this, you can see that the disk has a propeller subtracted out of it. And that's about all we need to do for geometry. So I closed out geometry. We're moving on to the mesh. So we can hit edit. What we're going to do here is we're going to create two body sizings for our two domains and two face sizings. I'll generate the mesh first. We can see how coarse it is before we make these changes to the mesh. Okay, great. So we can see it's pretty coarse there. We can hide this outer domain and make a section view. Okay. When we go back to mesh, we can see that it's pretty coarse. It's a pretty coarse mesh. We'll do the body meshes first. I'll undo this. Do a body sizing. Our first body is the outer domain. Element size is 0.025. Our second body sizing is the disk. and the size of this is 0.02. On to the face sizing. So to do that, we can hide different faces with F8, and we can box select the propeller. We want ANSYS to focus in on the propeller because it's the part that really gives us more detail. Mesh, sizing, 18 faces, yep, that's our propeller. 003. And then the other face sizing we're going to do is the interface. So we'll select these faces. Element size of 002. Okay. We also want to do this on the other side. So for the outer domain, we can box select this to select everything, and we'll go back to face sizing 2, and we'll hit Control, Apply. So it only has 3 faces, we want all 6, so I'll go back to the disk, single select. Okay. And so we know that this face sizing now has 6 faces. This is because we want that interface to have the same mesh so that it can talk to each other. That's also why we want to have a denser mesh at the interfaces. And so when we hit generate, we'll be able to see that it is denser at that interface and also denser at the propeller. The meshing is done. You can see that this outer domain has a denser mesh than before, and when we hit that section plane from before, you can see that the mesh gets much denser at that interface and also at the propeller. That's it for the meshing part of this. The next part is the naming selections. Now this is pretty important, we found, because sometimes the setup does not recognize certain parts if you don't name it right. So first we will have a pressure inlet. Pressure outlet. You can see them showing up here. We can do the interface. We'll name this interior domain interface. But you really need the interior in there. We will do the same thing for this inner surface. And we'll do one more for the propeller. It just helps us specify the source when we come to the acoustics part of this. And so that's all we've got for the mesh. Guess I can show all. Yeah, that's all we've got for the mesh. Okay, so now that the mesh is done, we can move on to setup. And if there's a yellow lightning bolt next to mesh, you can just right click it and hit update. But we start the setup. Okay, so our zones have loaded. So we'll click on display to see the mesh. You can hit edges. Great. So our units are going to be RPM, revolutions per minute. Solver is transient. We found that the Viscous model K omega worked fine. And finally, the acoustics. So the acoustics has two models. There's the FWH model and the broadband noise sources model. The broadband noise sources model will give you a overall profile of the acoustics for the propeller, whereas FWH will tell you, define the source of your sound and the receiver that you want. And so we can say that our source is the propeller, and the receivers are specify the locations in X, Y, and Z. I can put one at below the propeller by 1 meter, 2.5 meters, 5 meters. And we'll hit apply. Oh, and ANSYS wants us to compute simultaneously. Okay. For materials, we want air, cell zone conditions. So if you recall, we had a name selection that started with interior. This is where you will see its effects. So if you have a fluid and a solid, then issue there is that ANSYS is not recognizing that the disk is inside of the outer domain but still has the same fluid. And so to make this disk rotate, we can open it and say mesh motion, and the y-axis is 6,000 revolutions per minute. For propellers on a quadcopter, they range anything between 5,000 and 15,000. The outer domain does not change. Boundary conditions, we have pressure inlet. Our interfaces are automatically recognized. Our internals are here. Pressure outlet, walls. Mesh interfaces are automatically created. We'll go to monitors, residual. So we can initialize using standard initialization. Okay. So in order to get contours, we're going to have to make a few planes. We go to display, we can show the propeller. We'll create a plane in the middle of this propeller, XZ plane, and another plane in the XY plane. So we can take a look at those. It's showing the mesh right now. And so in results, we're going to want contours. Contours of velocity make it easy to, I guess, diagnose what's going on. Okay. We'll go to calculation activities. We'll make solution animations. We can have a first, and then we can also make animations of different views as well. We'll name this animation 2. And we'll do animation 3. We can hit initialize again, and we can run a calculation to get a nice contour animation of the velocity specifically. So for good resolution, we can do 10 to the negative fourth. And then for number of time steps, we'll do 200. I'm going to hit calculate. This is probably where I will hit pause. The last time I did this, it took me approximately an hour to an hour and a half. So, now that the simulation has stopped running, we can go and see our contours that we made. So if we scroll down results, you can open animations, playback, and we can take a look at that top view. And we see the propeller spinning, and the air gets dispersed as it gets pushed outwards. and it slowly reaches a steadier profile. Okay, and then if we go to animation 2, this is a front view of the propeller spinning. So we see a little bit of colors at the corners of that interface between the two zones. This just means that we need a finer mesh if we want that detail, but overall, our air is getting pushed downwards as the propeller spins. Cool. So if you recall, this past simulation was 200 time steps at 6,000 RPM, and while this does give us a detailed contour animation, it's only about 0.02 seconds in real time. So to get a better reading of the acoustics over time, we're going to do another simulation of the rotating propeller at a slower speed of 1000 RPM. So first we'll go to our cell zone conditions. At 1000 RPM. And then we will go to initialize. We can run this calculation at 100 time steps with a time step size of 0.025, max iterations. Okay, this looks good. So at this point, I am going to pause the recording here as well, because this also will take a while. So as you can see, the calculation is done. This propeller has had more time to develop its flow, so you can see the straight flow profile. It's not super accurate because the time step size is large by comparison compared to the last sim. So to get the plot, we can go down, scroll down to FFT, which stands for Fourier transform. We will have it process the receiver. We'll choose a receiver, and we want to measure the sound pressure level against frequency. Okay? And so here is the graph of the sound pressure level against the frequency. What this basically is that sound pressure level is in decibels, and at each particular frequency, it'll say the decibel of this frequency is a certain amount, and you can combine those values to get the overall sound pressure level, which is, if you have a device that measures the decibels in the area, that's the number you will see on the screen. We can also write this information to a file and to be able to process it in a software like MATLAB or compare it against other plots, and so you can do that.